Afternoon, we're going to start in next 1 to 2 minutes.
Yes, start now.
Let's start. Okay, let's start.
A warm good evening to all. I'm Professor Christopher Selvin, Registrar HBNI, here to propose the formal welcome address for the inauguration of Advanced NMR Spectroscopy course, Part 1. Today is 23rd January 2023, the 126th birth anniversary of the great freedom fighter through the Indian National Army, through which the famous Jai Hind concept has arisen, is none other than Netaji Subhash Chandra Bose. Our country is respecting him by celebrating this day as Parakram Divas from 2021 onwards. On behalf of HBNI, I salute and pay homage to this great patriot for his selfless service and sacrifice. On this day, 23rd January, is a very important day for science also. In 1911, the French Academy of Sciences turned down the membership application of Nobel Prize winner Marie Curie. Later, in the same year, she won her second Nobel Prize in chemistry. And there is a great thing, she has buried twice. The same country which was rejecting Nobel laureate Marie Curie has given a great praise for the Pantheon in special mausoleum in Paris. Coming to the business, I extend a warm welcome to our chief guest today, the most respected and Padma Shri awardee, Professor Ramakrishna Vijayacharya Hosur, former director, Center for Excellence in Basic Sciences, Mumbai, and former professor of TIFR, a great biophysical scientist known for his expertise in NMR and molecular biophysics. Professor Hosur is the founder of NMR Society and a recipient of various awards, including J.C. Bose National Fellowship, INSA Young Scientist Award, etc. A perfect person for a perfect job. I welcome Professor R.V. Hosur for delivering the inaugural lecture on overview of NMR spectroscopy today. I welcome our beloved Dean and Vice Chancellor officiating HBNI for this inaugural function, who is going to address on the benefits of the NMR course. I welcome Professor Haridas Pal, Associate Dean HBNI, who is going to introduce the course to all the participants. I welcome our beloved Institute Chair Professors and other Associate Deans for the inaugural function. I welcome Professor Maitri, Associate Dean, HBNI, who is going to propose the vote of thanks. I welcome all the directors, deans, and faculty members, convener board of studies from all our CAs and OCC for this inaugural function. Most importantly, the course is meant for the students. I welcome all the students for the inaugural function. Knowledge is of no value unless you put it to practice. To acquire knowledge, one has to study. But to acquire wisdom, one must observe. This is a statement by Marilyn Firstrand. I sincerely hope and believe that course is going not only useful for you to gain credit, but useful for your research career to analyze your materials of interest. I wish you all a very useful course on NMR. Now, with these words, may I request Professor P.D. Nayak to present a bouquet to Professor R.V. Hosur as a token of welcoming him to this function.
Thank you, sir.
I now request Professor Pal to introduce the course.
Thank you.
Hey, come here. Come
Selvin.
here.
I think so.
No, you'll not. Come here, please.
Let me see.
Your camera.
Thanks, Professor Selvin. Respected Professor Hosur, our chief guest today, Professor Nayak, officiating EC and Dean HBNI, Professor Selvin, Registrar HBNI, distinguished invitees, all our faculties, colleagues, participants, and friends. A very good afternoon to everyone. We all have gathered today to inaugurate our dream online course on advanced NMR spectroscopy from HBNI. And it is indeed my great pleasure to briefly introduce this course to this august audience. Wow. So, considering the immense importance of NMR spectroscopy for structural characterization of organic molecules, complex biomolecular systems, as well as use of NMR spectroscopy in medical diagnosis, like in MRI, we all realize that at HBNI, we should introduce an online advanced NMR course, spectroscopy course, to benefit a large variety of students, researchers, and scientists. With this objective and with thorough deliberations, discussions in a steering committee constituted by VC HBNI, this dream course has taken its shape and we have formulated to cover all different aspects of NMR spectroscopy. This course is designed into 8 modules. I briefly just introduce these 8 different modules. First one is Introduction to Basic NMR Spectroscopy and NMR Instrumentation. Second module is Heteronuclear and Multidimensional NMR. Third is Special NMR Experiments and Techniques. Fourth is hands-on training and problem solving. Fifth module is biomolecular NMR. Sixth one is NMR in drug discovery. Seventh one is solid-state NMR. And eighth one is magnetic resonance imaging, its basics and clinical aspects. This total NMR course is planned to cover in 80 to 85 hours course, distributed almost equally into 2 parts. I'll say part 1 and part 2. And the courses will carry a total of 8 credit points. We'll have 3 lectures per week, and each lecture will be of 1 hour duration. Initial 4 modules of the course will be taken up in part 1. It will start from tomorrow, that is 24th January 2023. And we wish to complete this part of part 1 in the first week of June, and thereafter we will conduct an exam for this part. Last 4 modules of the course will take up in part 2, which will start at the beginning of July, and we wish to finish it, complete it by October with an exam for this part. I am happy to inform you that about 140 participants all over India have registered to this course. I would also like to inform you that we have an expert panel of lecturers from both HBNI and non-HBNI fraternities who are all well recognized in their own rights through their immense contribution in the subject of NMR spectroscopy. Our expert panels of lecturers include Professor Arindam Ghosh, Professor Hoshur, who is our chief guest today, Professor Jagannathan, Professor Amit Chaudhary, Professor S.K. Ghosh, Professor Sudarshan, and Professor Sandeep. We are extremely thankful to all these lecturers to kindly agreeing to help us in conducting this course. Finally, we all hope that this course will be highly beneficial to all our participants taking part in this course that is offered by our National Institute. With this brief introduction to the course, I now hand over this charge to Professor Selvin to take it forward, these proceedings for today's function.
Thank you, Professor Paul. May I now request Professor P.D. Nayak, officiating Vice Chancellor and Dean of HBNI, to briefly tell about the benefits of the NMR course. Professor Nayak, please.
Good afternoon, and for my own behalf, I welcome all the dignitaries, our chief guest, Professor R.V. Hosur, Associate Dean here, Professor Decay, Professor Ghosh, Institute Chair Professor B.S. Tomar, our Registrar, P.C. Selvin, and online we have the Arindam Ghosh. He is one of our members in designing the course as well as one of the faculty in conducting this course. And many student participants who have taken this course, as well as many faculties who are also attending online for this inauguration function. In fact, all of you know that about the NMR spectroscopy and its beautiful applications in various domains. Realizing the enormous importance of NMR spectroscopy, both in academic and applied areas. We plan in HBNI to introduce advanced course on NMR spectroscopy. Main idea is to give a favor to graduate and postgraduate students and also take them to the advanced level in a part 2 of this course. This course also will benefit the young researchers, the faculties and scientists of various academic institutes, as well as industrial establishment all over the country. In fact, we have thinking at that time to conduct a postgraduate course in inorganic chemistry, and NMR course was a part of it. And because of some technical difficulty, we are not able to start postgraduate diploma in inorganic chemistry. And then we felt that it's better to start the most important part of that NMR spectroscopy. And for smooth executions and successful conducting this course, a steering committee was formed with Dr. H.Par as convener, Arindam Ghosh for NICER, Bhubaneswar as member, Professor Sunil Ghosh, Associate Dean HBN as member, Professor Amit Chaudhary, PMC as member, Professor V. Sudarshan, Mumbai as member, and myself. The course is designed by above members, along with Professor R.V. Asur, who is our chief guest today. Dr. Pal mentioned about the part 1, part 2, and what part 1 will contain and part 2 will contain. I will not go through it. We feel that this course intends to prepare the students and professionals self-reliant in dealing with various structure-based and conformation-related chemical problems, especially in regard to the material characterization involving complex molecular structures and polymeric systems encountered in chemistry and chemical industry. The course will be useful in understanding the application of NMR in various areas like drug discovery programs, biology, medicine, diagnosis of disease, imaging application in medical and non-medical fields, and so on. In fact, NMR is a very versatile tool, and all of you will agree with me that is one of the most powerful tools for chemists, biologists, biophysicists, and many more in area of medical and biological or related areas. Without taking much time, because we have our chief guest who is going to is expertise in this field and recently also published a book on NMR spectroscopy. I wish you all the student participants a very fruitful and stimulating day ahead with excellent faculty which we have selected from throughout India, not only from HBNI, but also from outside and HBNI faculty. And I once again thanks all of you, those who are present in this council or physically, as well as those who have joined online, and all the faculties who have agreed to deliver the lectures for this course. And thank you one and all.
Thank you, Professor Naik. Before going to the main talk, I'd like to introduce the chief guest of today. Professor R.V. Huzur started his scientific career in TIFR as a research associate in August 1978 and became a TIFR fellow in 1980 and continued till 1986. In between, he took a study leave for 2 years to do his postdoc research at Swiss Federal Institute of Technology, Zurich, from 1981 to 1983, where he worked with two Nobel laureates, Professor Richard R. Ernst and Professor Kurt Wuthrich. Professor Huzur rejoined TIFR in 1986 as a reader and promoted to associate professor in 1991 to professor in 1986 and a senior professor in 2023. He was the former director of CEBS during 2009 to 2017. Professor Huzur has immense experience in NMR spectroscopy. In his research career, he has published more than 200 papers, 3 books, and produced more than 20 PhDs and a couple of MSc students. His publications has a credit of Hutch index of 30 and ITER index of 104 and more than 3,844 citations. And most of his students are working as postdoctoral fellows in leading countries such as USA and UK. And very many people are occupying good position in leading institutes such as IITs. He is a recipient of various awards. A few of them are here. Young Scientist Award from Bruker Corporation in 1983. Young Scientist Medal from Indian National Science Academy in 1984. J.C. Bose National Fellowship from Department of Science and Technology, Government of India 2007. Professor G. N. Ramachandran Gold Medal from Council of Scientific and Industrial Research in 2009. And Fellow of International Society of Magnetic Resonance in 2013. And I found there is a lot of list. I just selected few only. He is also the Fellow of Indian Academy of Sciences, Indian National Science Academy, and National Academy of Sciences, and the Academy of Sciences for the Developing World TWAs. The Government of India has honored Ramakrishna Huzur with the Padma Shri in the year 2014. So with this brief introduction, may I now request Professor Huzur to deliver his talk on the overview on NMR spectroscopy. Professor Huzur, please.
Good evening. Can you hear me? Is it okay? Am I audible? Yeah. Good. First of all, let me thank Professor Naik for the invitation to come and participate in this advanced NMR spectroscopy course, which they have introduced this year and is going to be the beginning, and they will have many more in the future years. It's a very good initiative, and I would like to thank Dr. Paul for making all these arrangements and the invitations, and Dr. Selvin for introducing me to the audience here. NMR, as most of you know, is all over the place. Whether it is physics, chemistry, biology, medicine, engineering, everywhere it is there. So it is such an indispensable technique that one cannot live without it. So any course that one goes through, whether you take a graduate course in physics or a graduate course in chemistry or a graduate course in biology, we need to study this course. In fact, I happen to teach this to students in chemistry as well as in biology in IIT Bombay, and I've been teaching this at TIFR earlier and also at CBS. So this is a kind of a technique which is indispensable for most researchers and those who want to work in industries for various kinds of applications as well. So therefore, it is a very good initiative. I congratulate HBNI for introducing and starting this course for the benefit of all the students and the faculty and the researchers who would like to make use of this for developing their products and innovate and create some new systems. So my objective here is to give an overview of this technique, which is going to be covered in the next 80 hours or so, I've listed here my 3 affiliations as an acknowledgement to these 3 places, and it is because of them I am there where I am. So it is TIFR, CBS, and Biosciences and Bioengineering in IIT Bombay. Okay, so begin with, and to give a little bit of the history of this technique. The nuclei have a property known as nuclear magnetic moment. They also have a property called as nuclear spin. The nuclear magnetic moment was discovered by Otto Stern during the Second World War time, even before. But of course, he got the Nobel Prize for it in 1943. Subsequently, Rabi discovered the nuclear magnetic resonance phenomenon in the gas phase. This was again done in the 1930s. At the time when the war broke out, things could not progress, could not be recognized, but he was recognized in the end in 1944 with a Nobel Prize. Then Felix Bloch and Edward Purcell, both working in different places, they independently discovered this technique in the solution phase in the condensed matter, and they won the Nobel Prize again in physics. All these 4 Nobel Prizes were in 3 Nobel Prizes were in physics. And you can see then, of course, it was in the domain of physics, and people were interested in studying the magnetic moments and the properties of the nuclei and how this nuclear magnetic moment varies from nucleus to nucleus, and try to understand the theory of all of those ones. So to give a brief introduction to that theory, so we'll begin with what is known as the nuclear spin. Every nucleus has what is called as the spin, is an angular momentum, spin angular momentum. This is a quantum mechanical phenomenon. And related to that is the magnetic moment. They are related. Do I have a cursor here? Yeah. There is a pointer, is there? Is this a pointer? Because I want to show this. Yeah.
You can use this.
I can use this, yeah. I can use this. Yeah. Nuclear magnetic.
If you want to use any pen or
that will be better. Yeah.
red color, laser pointer.
Laser pointer, yeah, this is better. So you have this magnetic moment, a nuclear magnetic moment. This is a vector here. It is related to the spin angular momentum, which is represented by quantum number I. This is called the angular momentum quantum number here. So there is a proportionality factor which is called the magnetogyric ratio. So this is mu is equal to gamma I. And in quantum mechanics, we know that this nuclear spin can take discrete values like 0, half, 1, 3/2, and so on and so forth. And the magnetic moment itself is related to this. Of course, there is a magnitude of the angular momentum. This is root I into I plus 1 h cross. And that is when you measure the magnetic moment, of course, you will have that property there. But it is here is represented as a vector. Now, when you have an ensemble in your system, of course, there are magnetic moments which are in various orientations. And that comes from the principle of quantum mechanics. Notice here that, of course, we are talking about interface of physics, chemistry, biology. So it starts with the physics and then goes into the chemistry, then goes into the biology. We'll try to cover all of those ones here. So in the absence of the magnetic moment, any magnetic vector, magnetic moment can be oriented in any direction in space. That's because of the principle of superposition of quantum states. And then when you apply a magnetic field, for example, if I take a nucleus with a spin of half, it will have 2 possible orientations, parallel to the magnetic field and anti-parallel to the magnetic field with a certain angle here, because there is this magnetic moment. Z magnetization is quantized also. It takes certain integral values, and that is represented by the magnetic quantum number m, which can take values I minus 1 minus I to plus I with integral values of 1 in between. Therefore, for a spin of I is equal to half, m will take 2 values, half and minus half, and therefore it will have 2 different orientations, and there is all these vectors will be oriented at a certain angle with respect to the magnetic field. And we also know that these ones now will have different energies because they interact with the magnetic field, and the interaction with the magnetic field will depend upon the orientation with respect to the magnetic field. Okay, so this is symbolically represented the nuclear spin if they're rotating like this, but this is a concept. Okay, So now, and these two states which are oriented parallel are represented and antiparallel are represented as alpha and the beta states for I is equal to half. By and large, in most chemical and biological problems, we deal with I is equal to half. Except in certain cases where you go to material science, then you may deal with systems with I is equal to 1, I is equal to 3 by 2, 5 by 2, and so on and so forth. For most chemistry and biology, you deal with systems which are I is equal to half. And I list here some of those nuclei which are I is equal to half. You have the proton, and this is half, and this is the most sensitive of all the nuclei because the magnetic gyro ratio has the highest value here. And this is 100% natural abundance here. The deuterium has a spin of 1, and boron is 3 by 2, carbon 13 is half, oxygen 17 is 5 by 2, F19 is half, silicon is half, P31 is half. So mostly for chemistry and biology, we'll be mostly dealing with the proton, carbon 13, nitrogen 15, nitrogen 15 is not listed here. Okay, nitrogen 15 is also half, nitrogen 14 is 1. Okay, P31 also we will deal with, that is half. And their magnetic moments are also listed here. Notice that some of them have a negative magnetogyric ratio. This also is true with the nitrogen 15. And you have for those ones different energy, in the sense that the energy levels will get upside down. Okay, what's the principle of NMR? So we have the magnetic moment, which is interacting with the field B0, and therefore, because of the interaction, the energy, they will have different energies, then the energy separation will depend upon the magnetic field strength you have here, and this is schematically represented like this. One which is oriented parallel, this comes down in energy because of the minus E is equal to minus mu dot B0, minus should be there. And this has lower energy, and the one which is anti-parallel will have the higher energy. And the populations of these, when you have an ensemble, they will be distributed between these two states, and that is dictated by the Boltzmann statistics. Now you will see here that if at a particular magnetic field, energy separation is like this, okay, then if you supply energy which corresponds to this separation, there will be absorption of energy, and that is your NMR signal. That's the frequency. The intensity is proportional to the population difference between the two levels. Now, classically, one can describe it in a different way. That was a quantum mechanical description. You can also describe this in a classical way. This is actually what Felix Bloch did in the initial state. Edward Purcell actually used the quantum mechanical picture, and Felix Bloch was looking at in the nuclear classical picture, in the sense that he looked at the interaction between the magnetic field and the nuclear spin and magnetic moment, and it turns out as a result of, again, quantum mechanical principles, that there is the precession of the nuclei around the direction of the magnetic field. Whether they are oriented this way or this way, they precess around the magnetic field in a certain frequency. Okay, and that interaction frequency, of course, the frequency will depend upon the interaction strength. This is known as nuclear precession. They will go in the same direction, which is like this. Okay, and this is the E is equal to minus mu dot B naught, and this will also go like this. Okay, and if you see, they are in a cone, on the surface of a cone, whether they take the top half or the bottom half, they are on the surface of a cone. You cannot predict which portion of the cone is populated or not. All of them are equally possible. Therefore, the whole surface of the cone will be filled, whether it is top or half at the bottom. Now, if you take projections of these magnetic moments on the three axes, the z-axis and the xy axis, and you will notice that for every one direction in the xy plane, there is an opposite direction in the xy plane with equal strength, and therefore they will all cancel. Whereas the z components, they will not cancel because there is more population here than it is here. Therefore, there will be a certain net magnetization which will be along the z-axis. So typically, one calls this as the macroscopic magnetization, which will be oriented along the z-axis or the magnetic field axis. At equilibrium, therefore, there is no magnetization in the xy plane, and there is no phase coherence among the spins. What I mean phase coherence? If there is a certain relationship between the orientation of one spin on the surface of the cone with respect to another spin, then we say there is a phase coherence between them. And then in that case, of course, if there is a phase coherence, there will not be total cancellation. Then you may generate some transverse magnetization. That if you see a transverse magnetization is a result of a phase coherence of the spins in the ensemble. Okay, now what you do is, okay, consider this nucleus which is precessing like this, magnetic moment which is precessing like this, and I represent the same figure here once more. You apply a radio frequency field which is 2h1 cosine omega t. Because this is the radio frequency. This h1 is an amplitude which is actually quite small compared to the main field here. Okay, this is the radiation, this is electromagnetic radiation. Okay, so we're considering the cosine, the magnetic component of that one, so 2h1 cosine omega t, and this amplitude is extremely small. That is applied on the transverse plane here, in the xy plane. So you consider this cosine omega t, you can break that up into two rotating fields, e to the I omega t plus e to the minus I omega t. These represent two rotating magnetic fields. One goes in this direction, other goes in this direction. Therefore, the one which is going in the same direction as the nucleus spins is what is relevant for us because of the interaction. The other ones, the spins will not be able to see because it goes too fast. And this is in the radio frequency regime. So the energy separation is in the radio frequency regime, and these frequencies are also in the radio frequency regime. Now you can sit on one of these radio frequencies and look at the spins which are going around, which are precessing around the magnetic field here. It will mean that if you have the same frequency, then we say we have got a resonance condition. Under those conditions, the spins will appear stationary to the with respect to this RF field. And then what will happen? There will be interaction between that magnetic moment and this field, and therefore the magnetic moments will tend to tilt along the H1 field. They will shift away from the z-axis and move to the transverse plane. So if you do that, it implies then that we created a kind of a phase coherence between the spins. Therefore, the application of the RF creates a phase coherence among the spins. It generates an RF magnet, is a transverse magnetization. Now, in terms of the energy levels, then if there is interaction between the two, there will be change in absorption of energy, which means there is a spin flip. Alpha state goes to the beta state, and there can also beta state going to the alpha state. But there will be overall, there is more spins going to the beta state from the alpha state, and then there is absorption of energy. So that is called as the resonance absorption. Okay, so that is the physical principle of the technique, of the nuclear magnetic resonance technique. Now, for chemistry, it becomes important to study the structures of the molecules. But if all the nuclei have the same magnetic moment, then of course it doesn't make too much of impact. However, there is an important property called as the chemical shift. The chemical shift means that each nucleus is surrounded by a certain electronic cloud around it, and the electronic cloud can vary from one system to another system or one nucleus to another nucleus, and therefore it can see the magnetic field differently. In other words, we will say that if you have an applied magnetic field B0, this magnetic field is screened by the electronic cloud. How does that happen? Well, the application of the magnetic field generates certain currents in this electronic cloud, and these currents will produce a magnetic field in turn that is called the induced magnetic field, and that will tend to oppose the externally applied magnetic field. Therefore, the effective field seen by the nucleus will be B0 into 1 minus sigma I. Sigma I is called as the screening constant. Okay, and therefore the Bi will then vary depending upon what is the screening constant, and this is where the importance of magnetic resonance comes in. And you define a certain kind of a number which is called as the chemical shift here as delta I is defined as nu I minus nu R divided by nu naught, where nu naught is the mean spectrometer frequency, which is like 100 megahertz, 200 megahertz or whatever. Then you have a reference molecule here which is called, and it absorbs energy at a particular frequency called nu I and nu R, and then your own frequency which you are investigating is nu I, and you take this ratio, you get a number which is called delta I. Now this is actually in ppm. You have to multiply by 10 to the power 6 here because this one is in kilohertz range, this is in megahertz range. So when you multiply by 10 to the power 6, you get a number which is something like 0 to 10 or to 100 and things like that. Otherwise, it is much smaller number. But this is the so-called the chemical shift. So higher delta implies a higher indicating downfield shift and vice versa. This is the nomenclature. So basically, depending upon what the chemical shift of the particular nucleus is, you have information about the structure of the electronic environment, which in turn tells you about the structure of the molecule. There is another important property. Okay, now here I'm telling the same thing here. You take this particular molecule, this is vinyl chloride, you have three protons here, and there is a chlorine group here. Okay, now the chlorine has a property of is an electronegative group, electronegative, and therefore it pulls out electrons towards it, as a result of which the electron density around this proton, and this proton are going to be different, and they'll be affected differently because of the distance between this and this through the chemical bonds. The worst which will be affected will be this, so electron density will be low here, therefore the screening will be less here, therefore it absorbs energy at the highest frequency. So we call it as a nu B, and accordingly other ones also will be different. This is followed by nu A and then followed by nu C. So you get 3 lines here, nu A, nu B, nu C. So this tells you about the structure of the molecule. Now, so therefore, depending upon the structure of the molecule, you have chemical shifts appearing at various frequencies. And this is for the proton, we write it in terms of 0 to 10, 12 ppm here. And that is, I already defined to you what is this delta value, 0 to 12 ppm. Different kinds of groups have different kinds of chemical shifts here. If they're electronic withdrawing groups, they will appear more downfield here. Maybe we should put off this light. Is it better? Even I'm not able to see those numbers. This is better. This is better. So now you can see various kinds of groups here. A CHO, a CH3, okay, CHCH. So are of these various kinds of groups. The red one is the one which you are monitoring. See, depending upon your functional groups and what is the structure of the molecule, you will have different kinds of chemical shifts. That is indicated here. See, various kinds of, and this is for the carbons. This is for the protons, and this is for the carbons. Different kinds of carbons, aliphatic carbons, aromatic carbons, and the carbonyls. Carbonyls appear much more downfield. And this carbon chemical shift goes from all the way 0 to 200 ppm, always with respect to some reference molecule. Typically, tetramethylsilane is used as the reference compound for calibrating all the chemical shifts. Okay, so for those which are soluble, not soluble in water. If they're soluble in water, of course, you have different kinds of reference compounds. But point is, you have different kinds of chemical shifts for different structural environments, electronic environments. This provides a very useful input for the chemist to characterize their molecules. When they synthesize something, looking at the NMR spectra, they can actually figure out what sort of groups are present. If they intend to design a organic molecule with the aromatic rings, of course, you must have chemical shifts at 100 ppm, and these are the aliphatic ones which you will have. What is this? This is 150, isn't it? 50. This is 150, this is 200. So, okay, now here are the aromatic ones. And here you have the carbonyls and the aliphatic ones will be here. Okay, now there is a next property which is called as a spin-spin coupling. That is, the protons are not only in the magnetic field environment differently, but they also interact with each other. So you have the red and the blue, they interact with each other, and because of this interaction, they absorb energy at 2 different frequencies. And this proton, for example, absorbs at 1 energy, depending upon whether this proton is oriented parallel to the field or anti-parallel to the field. So therefore, you will have 2 lines. And similarly, this proton also will have 2 energies of absorption, depending upon whether this proton is parallel to the field or anti-parallel to the field. 2 different orientations. And this interaction happens through the electrons in between the compounds, like through the bonds. So they polarize through the electrons and things like that. We will not go into the mechanism of that. That will be taught during the course. So you will have 2 different lines for each of these protons. So if you have more number of such ones, you will have more number of lines. For example, if you have ethanol here in D2O, you have 3 protons here, 2 protons here, and 1 proton there, and all of them are coupled. And therefore, you see the CH3 group will appear as a triplet. This is coupled to 2 protons here, and the CH2 group will appear as a quartet here in the ratio 1:3:3:1, and the OH proton will appear also as a triplet, typically because of the coupling to these 2 protons. Okay. Now, of course, here CH2 protons will have the coupling here as well as here, but that you don't see the separation here so clearly on this one. Otherwise, it is a multiplet. You will have interaction with this and also with this. By and large, one does not see this splitting the OH group. This is because of the exchange with the water. By and large, you don't see this, and you will have a single line here, but a broad line, and you will see these separations quite clearly. So you will see multiple lines in your NMR spectrum. So the multiplicity is one thing, chemical shift is another thing, and each of them carries an information about the structure of your molecule. Okay, now how do we measure this? How do you, a priori you do not know where these absorption frequencies are. So what you do, you have a particular field, so you sweep the field, keep the constant frequency, or you can keep the field constant and sweep the frequency. In either case, you can find a resonance. So by and large, in the early days, one used to use the sweeping of the field procedure because that is easier to do it, because the magnets were of electromagnet type. In the electromagnet, the field can be changed simply by changing the current through the coil, which is going around in the magnet, and therefore it is easy to change the field. And that is what was used. Now, the population changes have to follow the rate. Okay, now I go back here. No, sorry. So you see here, these intensities are proportional to the number of protons. This is 3 times intensity of this overall integral of this one. This is 1:2:3. That is the kind of an intensity ratio you will have. Okay. So now the population changes, you'll have to follow the field changes. Okay. What does that mean? If I change the field, the populations will change. Now, if you want to measure the system at equilibrium always, you will have to allow time for the system to reach to equilibrium, and that will take some time, and that is dictated by what is called as the spin lattice relaxation time, T1. This can vary from a few hundred milliseconds to several seconds, and you'll have to follow the changes in the populations. That means you'll have to sweep the field rather slowly, and this is the rate at which it will change the populations. So for example, if t is equal to infinity, then n will become equal to n naught. So if t is of the order of 5 times t1, then it is almost close to n naught. N naught is the equilibrium population difference, and n is the population difference at any point in time if we change the field and allow it to reach to the equilibrium. So if I have a sweep rate of 1 hertz per second, let's say, then a time per sweep of 1,000 hertz is 16 minutes. So it takes a lot of time. This is how it was done in the early days. And your signal to noise in your spectrum is defined in this manner. You have a peak height above a mean noise level divided by the peak, maximum peak minus peak separation in noise multiplied by 2.5. And this is the signal to noise ratio. And this used to be very, very small. So what do you do to increase the signal to noise ratio? You will have to scan several times and add the data. When then you have the signal to noise ratio, which will be increased. So signal to noise ratio is dictated by the number of sweeps co-added, and it goes at the square root of that one. So a signal to noise enhancement of a factor of 10 requires 100 sweeps to be collected. That is 1600 minutes. And this is a lot of demand on the spectrometer. There's issues of stability of spectrometer, stability of the samples, then high concentrations are required, difficult to observe low abundance nuclei such as carbon-13, hydrogen-15, etc. Therefore, initial stages were very, very, while the discovery itself was very exciting, but people found that okay, applications can be very limited because of these sensitivity issues. So then what happened was, well, maybe NMR is not as useful a technique as one thought it to be. Okay, now, so therefore people actually shifted from NMR to EPR because the EPR sensitivity is 2000 times higher than that of proton from the new NMR, and that is thought that we shifted. However, then there was a revolution here, and that is called as the pulse excitation. In this case, actually the measurement technique is changed. You don't sweep the field. You have this RF, you have the constant field, and you have the RF at a particular frequency applied for a short time. This time is of the order of few microseconds. Okay, you have the RF which is here, you applied for a short start here, and then cut it off here. So it is applied for a short time. Then what happens is the response is you generate a whole range of frequencies here. This is the frequency response to this time input. RF input, you get the frequency response like this. It generates a whole lot of frequencies with the different amplitudes. This is your main omega naught, that is this frequency here. And around that omega naught, you have a whole range of frequencies generated with different amplitudes. For example, this point is 1 by tau. If tau is 10 microseconds, this is of the order of 10 to the power 5. So that is 100 kilohertz. 100 kilohertz here, 100 kilohertz here is quite a large width. So you have 200 kilohertz range you have. Of course, we don't want to use this much region. We want to use a very small region here because we want to have a uniform excitation for all the spins. So you use a small portion here which has the same amplitude. All of those frequencies are nearly similar amplitude. then about 10 kilohertz if you use, that's good enough. 10 kilohertz is also quite a lot. For 100 megahertz, 10 ppm is 1000 hertz. So therefore, for a 500 megahertz, 10 ppm is 5000 hertz. Therefore, it is quite sufficient to do it that way. So what you do is then you do a filter here, put it and select the frequencies only from this area, and you excite all the frequencies which are required for you in your NMR data collection. Okay, what this small application is also called as a pulse. Therefore, since applying for a short period, it is called as a pulse. And this relationship here is represented by the Fourier transform. This time domain function is related to this frequency domain spectrum by the Fourier transform. Okay, now this RF does something else. The RF also rotates the magnetization out of the z-axis. So if typically this rotation is given by this particular equation here, minus gamma h1 times tau, this the h1 is the amplitude over RF, gamma is the magnetogyric ratio, tau is the time for which you apply. If this angle is 90 degrees, then the magnetization will rotate by 90 degrees. If it is 180 degrees, it will rotate by 180 degrees and so on and so forth. Therefore, accordingly, we call it as a 90-degree pulse or 180 pulse and so on and so forth. And this happens in this direction. If I apply the field along this axis, it will rotate into this axis. If I apply the RF along this axis, it will rotate from this axis and so forth. Therefore, we call it as an X pulse or a Y pulse and so on and so forth. Okay, what happens after the application of the RF pulse? Now you remove the RF, so there is no magnetic field. So therefore, what happens? So you have brought the RF, the magnetization to this transverse plane. Now, since there is no RF, it has to return back to equilibrium, and then it will do so by precessing in the transverse plane, eventually recovering like this in this kind of a spiral manner. So it goes up here eventually, and then when it does so, all the individual frequencies go with the respective characteristic precessional frequencies. And therefore, and you put the detector here, the rotating magnetization will induce an voltage into your detector system. Therefore, you get a signal here. And this will be time dependent, and the different frequencies will produce different signals. So what you will therefore observe as a signal in the detector is the superposition of the frequencies generated by the individual spins. Therefore, you see this is the superposition of two frequencies, and we call this as an FID. This is called the free induction decay, because this is the induced signal, and this is the decay because slowly the phase coherence in the transverse plane will disappear, and then of course it will cause a decay. There is also a decay of the magnetization for other relaxation processes, which is called as T2 relaxation. Okay, now clearly you can see that this free induction decay is a Fourier sum of the frequencies which are present here. So therefore there is a relationship between the free induction decay and your NMR spectrum. This is the NMR spectrum. This is related by Fourier transform. Now what we have achieved in this process, see the process is you applied for the RF for a 10 microsecond time, and you collected the FID for 100 milliseconds, and all the signals are detected at the same time. And the Fourier transformation will take about 10 seconds or something like that. Today it will take even less. Okay, so therefore now in 1 second, less than 1 second, you collected the entire spectrum, which was 16 minutes earlier. Okay, now therefore you can signal average many times, so you add here 500 scans. Okay, this is the spectrum of this molecule here done by the Fourier transform NMR, and you got a spectrum like this. The conventional spectrum was like this. So when Richard Ernst, this was the person who was the inventor of this technique, Richard Ernst, and Anderson, when he was working in a very young company when he did this. And actually Richard Ernst told me that this paper was rejected 3 times. Why was it rejected 3 times? Because they did not get a signal like this. So therefore, they said this is not correct. You got some junk there. So, but however, eventually the truth stood out, and then they got, it was published in Reviews of Scientific Instruments at that time. He was trying chemical physics letters, Journal of Chemical Physics, and so on and so forth. It did not go. But it went here. Now it has caused a revolution. Therefore, you see, he won the Nobel Prize for this in 1991. The Fourier transform NMR spectrometers used to look like this. This is the electromagnet. At that time, it's the electromagnet. Okay, still, and this is the console. Now you have a computer automatically built in, because you need to control for how long you want to apply the RF. You need to be able to Fourier transform. All of these are now digital processes. And therefore, the computers have entered the spectrometer, and you have the magnetic field, which is generated by the electromagnet. Okay, the electromagnets have a limitation as to how much you can go into the strength. As you have seen earlier, that the strength of the magnetic field dictates the sensitivity of the spectrometer. So therefore, you want to increase the magnetic field. How to increase the magnetic field? Now, electromagnets cannot go too far. because slowly energy dissipated there will heat up the magnet, and then of course the properties of the magnet will be destroyed. Now came the next thing, superconducting magnets. What are superconducting magnets? So here is a picture of a superconducting magnet. This is a 20 Tesla superconducting magnet here. It looks like this. So you have a superconducting coil here, and this is immersed in liquid helium, and therefore it remains in the superconducting state. Superconducting state means once the current keeps flowing, this is the coil, closed coil. And if the current going there, never it doesn't dissipate, keeps going forever. So when the current is going like this, it will generate a magnetic field, which is rock steady because there is no disturbance. There should be no disturbance around. And then it is a very stable magnetic field you will generate, and you can increase the current depending upon the nature of the material which you have here. And you can actually go up to 20 Tesla, 21 Tesla, even more. Higher magnetic field strength can be created. So, but you have to keep pouring helium, liquid helium. So therefore, this is at 4.2 degree Kelvin, and you have a chamber which is surrounded around it, which is a nitrogen chamber, liquid nitrogen chamber, because it has to be absolutely insulated. It has to hold on the liquid helium for long. And then you have here the vacuum chamber here, and the vacuum is of the order of 10 to the minus time tower here. So therefore, insulation is extraordinarily good. Today you have these magnets which can hold helium for almost 1 year. If you take 500 magnet or 600 magnet, you don't have to fill helium within a year. So therefore, such wonderful magnets are come up. This is all technology which has developed. Okay, and then you see how you increase the strength of the current. Increase the number of turns here, and increase the length of the coil. And this is done by absolutely wonderful ideas with regard to the superconducting wires. And there are kilometers of superconducting wires inside this magnet here. Therefore, in several turns, the superconducting wire is built in here, and that produces an enormous amount of current, and therefore you have a very high magnetic field. Okay, now, so that is so much for the instrumentation, the technique. Now, much of the development in NMR has happened because of its application in biology. And the chemistry, of course, did contribute to the lot, but of course, there are smaller molecules. But the larger molecules posed a greater challenge, and that was the proteins. Initially, people thought that NMR should be applied only to small molecules like organic molecules. But however, a revolution came up when it was applied to the proteins. This was done by Kurt Wittrich in Zurich, and of course, he won the Nobel Prize for it in 2002. Much of the developments that have happened in NMR spectroscopy, both in terms of the hardware as well as software, and regard to the NMR theoretical sequences, happened because of the applications to proteins. Therefore, I run through these proteins applications, automatically other things will follow, other things will become easier to understand. Now here is a protein NMR spectrum of a particular protein which has 130 residues. This is of lysozyme, 129 amino acid residues. You cannot count how many signals are here, okay? Thousands of signals. Now, and for any analysis of NMR, you have to identify the individual resonances to particular kinds of protons. Then only you can study the interactions between them. And this is an extremely complicated NMR spectrum. Then how do we take it forward from here? And that's where another revolution came up. This is a two-dimensional NMR. And this was again came from Richard Ernst. Of course, the idea was also put up by Jane Jenner from Belgium. It was exploited maximally by Richard Ernst and Kurt Wittrich. And the two-dimensional NMR typically looks like this. So you have two frequency axes here. This is the omega 1 and omega 2. And you have the diagonal here, which is the so-called one-dimensional spectrum. And you have lots of off-diagonal peaks, which are also called as cross peaks. And these are the carriers of information. They reflect correlations between the protons. As I said, you have the spin-spin couplings, the J coupling, or there can also be what is called as the dipolar coupling, through space coupling. And that also, there are two kinds of information which are there, which are now displayed as off-diagonal peaks in your two-dimensional NMR spectrum. Okay, how it is done? This is done in the particular way like this. So you have a certain preparation period, you prepare the spin system in a particular way, then you allow it to evolve for a certain period of time, which is called the evolution time, and you have a certain operation called as the mixing here, and the actual signal is detected during this period here. Now we repeat this experiment for various values of this T1 period. So that is schematically indicated here. The first FID is collected with this 0 T1, then certain T1, second FID, another T increment, the third FID, fourth FID, fifth FID. So you collect about few hundred FIDs, sometimes 512 FIDs like this. Okay. And then what does the mixing do? There is a certain information content in the spin system here, and the mixing transfers this information between the spins which are correlated in some manner. Either they are correlated by J coupling or correlated by dipolar coupling. The dipolar coupling means it is through distance, the dipole-dipole interactions, and either way one can do that. So depending upon the transfer of information, you generate two different kinds of correlations. And the correlation spectrum will look like this. So you have a diagonal peak here, the diagonal peak, and you produce a correlation peak which is showed schematically in the previous stacked plot. This will tell you that these two protons are correlated, okay, either through J coupling or through dipolar coupling. And signal is actually directed only this. So therefore, this period is called as the indirect detection period. The frequencies which are present will appear along one of these axes, which is called as the omega-1 axis or sometimes the F1 axis, and you have this detected signal appears along this frequency axis, which is called as the F2 axis or the omega-2 axis. And these were the two seminal papers which were published as 2D Revolution, Richard Ernst, two-dimensional cozy spectrum, application to nuclear magnetic resonance. This is the book which was, this is the paper. And he wrote a book also in the same kind of a type, Principles of Two-Dimensional NMR Spectroscopy. These are two seminal papers, Journal of Chemical Physics, again Journal of Chemical Physics, 1976. And here the J coupling correlations are displayed in the cross peaks. Here is the dipolar coupling correlations are displayed in the cross peaks. And this was published in 1979. Notice here J. Jenner, he is the person who actually generated this idea with two-dimensional spectroscopy, but it was mostly exploited significantly by Richard Ernst and Kurt Wittrich. So to illustrate this here, how it is useful, so you have a cozy spectrum, you take a plot here, this that are possible here. There are J coupling correlations are possible from this amide proton to this C alpha within the same amino acid residue, from this C alpha proton to the beta proton, then to the beta proton to the two CH3 protons. Okay, these are J coupling correlations. These are indicated in the dotted line, dotted contours. Okay, and these correlations are displayed in this spectrum. NH to the C alpha correlation here, H alpha to the H beta to the H gamma. So therefore, you will have all these correlations are displayed in the cozy spectrum. Therefore, by looking at these, you can actually identify, by connecting all of these, you can identify the spin system, you can identify the amino acid residue. So all the 20 different amino acid residues can be identified. Okay, now these thick lines here, these ones are not J coupling correlations, but these are dipolar coupling correlations, and these will appear in the so-called nosy spectrum. The nosy spectrum displays dipolar coupling correlations. Okay, this is the characteristic cozy spectrum of a DNA segment here. You have, this is the protein only. So this is the aromatic protons here. Aromatic protons are connected to some beta protons here. These are the phenylalanines and tyrosines and things like that. So here you have the NH protons to the alpha protons here. These are in this region here. And from the alpha protons to the beta protons to the gamma protons, you have all of these correlations in this spectrum. You notice here, so much of dispersion is present in this spectrum. You can identify these various correlations and identify the nature of the peptide, what you have here in your investigation. Okay, this is the nosy spectrum. The nosy spectrum displays dipolar correlations. And this is a simpler one. This has only this spectrum is, of course, one of the very early ones. Okay, now what does this tell you? It contains not only those which are present in the cozy spectrum, because they are also short distances, and the dipolar coupling is the intensities of the peaks here are proportional to 1 to the 6th power of the distance, 1 over 6th power of the distance. And therefore, this dies on fairly quickly. And by monitoring these intensities, you can see which protons are close by in space in your molecule. And therefore, within the amino acid residue, all the cozy peaks will also be present here. In addition, there are other peaks which are coming from long distance correlations. For example, if I have a polypeptide is running like this, you have this A, B, C, D. These are the 4 protons, let us say, which are located in these different places in the one-dimensional spectrum. Now, depending upon the way the protein chain folds here, so if it folds like this, then you will have a correlation between these 2 protons. If it folds like this, you'll have correlation between these 2 protons. And like this, it will have correlation between these 2 protons. Therefore, depending upon the way the protein will fold, you will have different correlations displayed in the 2-dimensional spectrum. And by quantifying this, you can actually estimate the distances to a reasonable accuracy, and that will enable you to determine the structure of the molecule. Therefore, the nosy spectrum is called as the fingerprint of the structure of your protein molecule, whereas the cozy spectrum is a fingerprint of the amino sequence in your molecule. Okay, then therefore, these are 2 inputs. You have dipole-dipole interactions, distance dependent, and you have the J coupling information, which is cozy from the spectrum. You have the correlate, but the torsion angles are determined from the J coupling information, and the distances are determined by the NOE interactions here. Okay, so you have a structured calculation algorithm here. You generate 2 limits for the distance between 2 protons I and J, the lower limit and the upper limit on the basis of the intensity. And on the computer, you build a model. So if your model has a distance which is between these 2, it is an acceptable distance. If it is not, then there is a violation. Now, therefore, you will have to optimize the structure to get these in between. So you define a potential function here. This takes care of the violations at the lower limit. This takes care of the violations in the upper limit. So you have both 2 contributions coming in. So you have to keep optimizing your model on the computer. Ultimately, you must get 0 or a minimum value when all the constraints are satisfied. So this is how the structure calculation progresses. And you can see here, this is an algorithm called a distance geometry algorithm, which generates the structure of the molecule on the basis of the distance constraints you generate from the nosy spectrum. Okay, you start with the 6 different initial structures. These are all stereo pictures, and you to remove the bias of the initial structure, you have to start from very different initial structures. And after having obtained all the distance constraints, you see you have finally the structure coming to be the same. So this will tell you that your distance limit constraint set is sufficiently good enough. Okay, this got him the Nobel Prize. Richard Ernst, 1991, and Kurt Wittrich, 2002. Okay, now we got into more complications. So your nosy spectrum became more complicated. So you have a whole crowding of peaks here. Now, how do you quantify these intensities to estimate the distances between the protons? As I told you earlier, that it is a protein NMR which has driven NMR development, technology development, pulse sequence development. So this is an illustration of those ones. So you have this difficulty here. There's so much crowding of these peaks. How do you identify these? Thousands of peaks, tens of thousands of peaks, not just 1,000. How do you identify this? So this became impossible. This is the similar limit as you go from 1D to 2D. Now you go from 2D to other things. So far we are talking about proton-proton, but now we can also use other nuclei like nitrogen-15. Here it is a nitrogen-15 proton correlation spectrum. This is a 2-dimensional spectrum. This is equivalent to taking only the cross peaks here. What are these cross peaks telling you? Amide protons here and the aliphatic protons here, right? So that is that one. So here you take amide protons here and the corresponding N15 chemical shifts. Okay, therefore it's a cross peak, heteronuclear correlation here, and you have, every amino acid has one NH group in the backbone, and therefore it produces one peak for you. You can count the number of peaks here. It will be equal to the number of peaks, number of residues minus the prolines, because the prolines don't have the NH protons. So you can therefore improve the resolution in your spectrum by making use of this in your spectrum. How do we use this? You combine this with your 2-dimensional nosy spectrum. Oh, there is one more. This is similarly you can do with the carbon chemical shifts. You have the protons here and the carbon chemical shifts here, the aliphatic ones. These are the methyls, and then you have the aliphatic ones. Then you have the alpha carbons, and all of this is very good dispersion here. Okay, so you make use of these ones to increase your dimensionality of your spectra and establish various kinds of correlations. A number of heteronuclear NMR experiments have come in. We will not go into all of these details, but important thing is for these experiments to work, you will have to produce proteins which are isotopically enriched. N15 enriched and C13 enriched. Okay, and this requires the biology. Now you actually produce your proteins inside your biological cell, the E. coli cells, which are fed with nitrogen 15 source and the carbon 13 source. And they will label all your proteins with nitrogen 15 and carbon 13, and you isolate the proteins from there, purified, and then you can start recording. These are called as triple resonance experiments. They will go into 3 dimensions now, 3 dimensions, 4 dimensions. And these establish correlations like this, establish correlations between this amide proton, this nitrogen, and this 2 C alphas here, this amide proton, and this C alpha nitrogen, and this C alpha here. So you can design various kinds of pulse sequences depending upon what correlations you want to establish. So these are our transfer processes. So these are multidimensional, multiple experimental sequences. You can transfer information from one nuclei to another nuclei. So for instance, here you have a proton-proton spectrum, a schematic, and you have a proton-nitrogen 15 correlation spectrum here. You combine these two to generate a 3-dimensional spectrum. You have proton-proton and nitrogen 15 here. And you can add on to C13 to generate a 4-dimensional spectrum, proton-proton, nitrogen, and C13. Therefore, you can clearly see there is so much of improvement in the dispersion of the peaks, and you can study the larger molecules. All those peaks were there in the 2-dimensional spectrum can now be dispersed into the various planes in the 3D and the 4D spectrum. So as a result, what? So you see, this was the 1980s, 1-2 protein structure in 2 years. Now you see here where it has come. Almost 13,000, 14,000, 16,000 protein structures determined by using these various multidimensional NMR techniques. Okay, now we have another challenge. So, well, when the protein is well folded, of course, you have no difficulty because the peaks are well dispersed. But if the protein is disordered, typically we now know there is a certain class of called as intrinsically disordered proteins. They don't adopt a structure at all. They adopt a structure when they bind to a particular kind of a ligand or another protein substrate they bind, but otherwise they don't have a structure. If you have a protein of that type, you can see here what happens, what change it makes. You have a folded protein, this is HIV protease. Folded HIV protease, unfolded HIV protease. The dispersion along the nitrogen and the amide proton dimension is completely lost. But however, the good thing is that the nitrogen 15 dispersion is still present here, all the way from here to here. You can make use of this to design experimental sequences to improve the dispersion in your spectrum. Here's an illustration that you have exploited nitrogen 15 dispersion along 2 dimensions. In a 3-dimensional spectrum, you put the amide protons here and you put the N15 on one axis and N15 on another axis. Now, if you generate experimental sequence like this, it's called as HNN, and this is, if you take a cross-section through this, at this particular cross-section, you will produce these 3 kinds of peaks. At a particular amide proton chemical shift, you see correlations to the nitrogen 15s of I-1 and I+1 residues along the polypeptide chain. If you took an orthogonal cross-section at the same N15 chemical shift, you will see these 3 peaks here. These are like the triplet filter through the HSQC. This is the correlation spectrum which I showed you earlier. You see 3 peaks at the respective NH chemical shifts and the N15 chemical shifts. So therefore, it is like a triplet filter through the HSQC spectrum. And then they have different signs. That's also another important factor. These are positive, these are negative, these 2 are negative. And it turns out that these sign combinations will depend upon what are the residues in the triplet. Whether there is a glycine or no glycine, it makes a difference. Okay, and that is an important factor. Then there you have another complementary experimental sequence called HNCN, which shows you have the corresponding one, you have the I and I+1, and in the F1, F3 plane, and in the F2, F3 plane, you have the I and I-1. So this provides a directionality for your walk along the polypeptide chain. Because in the earlier case, you wouldn't know which one is I-1, which is I+1, but here you will know which is I-1 and which is I+1. Okay, I told you earlier that you have different kinds of patterns of signs of the peaks depending upon whether you have a glycine or you don't have a glycine. So we will not go into the details of these ones, but the point to note is that you can have positive-negative combinations or positive-positive combinations. Okay, see here for positive-positive, positive-negative, negative-negative, negative-positive, and so on and so forth. These actually serve as checkpoints for you if you are walking along the polypeptide chain. From one particular residue, you go to the next residue, to the next residue, to the next residue. You hit upon a glycine, you must generate a sequence of patterns which are indicated here. So this makes it extremely easy to walk along the polypeptide chain without much difficulty. Okay. Subsequently, a large number of experimental sequences have been designed. Incidentally, I am only showing all those which are designed by us. There were many others which were designed by various other people, but I've included here only those which are based on HNN and HNCN. Okay, as a result of that, what happens now? You have a whole lot of experimental sequences generated. You also write a software to analyze all of things in automated manner, because it is, you know, the chemical shifts, therefore you can immediately jump there. The computer programming can take care of that one. You generate a sequence here, autobab, the software, and automatically assign the backbone in about 2 days. Backbone fold can be obtained in 2 days. So from the chemical shifts, you can generate a backbone fold through this certain other softwares which are there available today. Okay, now we can do even better. So there is another strategy which has happened, and this is you include what is known as non-uniform sampling. In the earlier case, I showed you that along T1 period, you have to collect 512 data points and things like that. That is extremely time consuming. But it turns out that you don't have to collect all those 512 points. You need to collect a small fraction of that. So 25% of those, or sometimes even 10% of those. And you can generate the other data points by computer kinds of simulations. By making use of certain algorithms, you can simulate that, and that will reduce your experimental time quite substantially. So in this, I'm showing you 3D experiments. Okay, this 3D experiment was recorded in just about 1 hour, 29 minutes. This was recorded in 28 minutes. This is recorded in 22 minutes. All the 3 experiments were recorded in about 2 hours. So these 3 experiments put together provide you all the chemical shifts along the polypeptide chain backbone. So using those chemical shifts, you can calculate the structure, and you can see the structure calculated here to the RMSD of 0.93 angstrom. This is an extremely good structure calculation for the backbone of a particular protein. Okay, so now I almost come to the end. So that was with regard to the development, with regard to the solution NMR spectroscopy, and how we did not go into the solid state NMR. Solid state NMR is now taking over to those proteins which are not soluble in water, and therefore you'll have to study by solid state NMR. And of course, the challenges in solid state NMR are still higher. The resolutions are not as much as in the solution state NMR, but they're trying various different kinds of approaches like hyperpolarization, okay, and selective labelings and things like that. And the last application which earlier one was talked about was the NMR imaging, and this is a completely different application. Is NMR spectroscopy only, but it is called as magnetic resonance imaging because you monitor the water content in the different parts of the body by imaging the system. And one makes use of so-called field gradients here. We will not go into the details of that. It's just an overview talk here. And so these people measured NMR signals indicating water distribution in your body. So if you have any cancerous growth or some other growth, then their water distribution is going to be affected. The relaxation times of water in these tissues are different, and therefore you can image them properly. And this led to the Nobel Prize to Peter Mansfield and Paul Lauterbur in 2003. So therefore, I have tried to cover here, starting from the basic principles, how the technology evolved, how the applications evolved, and how it has led from one to the other. The way to each one is driving the other. Applications drive the technology, technology drives the application, and so on and so forth. So I think I will come to an end. And some of those this is a general slide of all the students which have contributed to the developments which have happened with regard to the solution state NMR. And there are postdocs also, various postdocs who have contributed to the developments here. I would particularly mention about Veer Mohan, who is a part of the book which was mentioned. We recently published this book, Veer Mohan and myself. This was a graduate course in NMR spectroscopy. This was a postdoc with me for about 5-6 years. Now he is working for a different company. He has also started using artificial intelligence in NMR. Deep learning and artificial intelligence, that is a new thing which is coming up now. There is a new buzzword, how to improve the spectra, how to design pulse sequences using artificial intelligence and deep learning. And this is a new application which is going to revolutionize further the technology of NMR. So I think I will stop here once again, and thank you for organizing this workshop and giving an indication to the students that what all NMR can do. And it is indispensable, whether you are doing physics, chemistry, biology, medicine, this is important to learn all this. So thank you so much.
Thank you, Hosur, for your enlightening talk,
Getting cool.
overview of NMR spectroscopy. So now, as a token of our love and appreciation, I request Professor Paul to give a small memento. Some I request Professor Naik to give to the may I request save the dignitaries. Request some of the dignitaries to have remarks on the NMR course, please. Like some of the dignitaries to make some remarks about the NMR course.
Yes, in fact, our former Vice Chancellor, Professor Rao is there. P.R. Vasudeva.
Sir, Professor Vasudeva, you're there? Like to hear from you, sir?
Unmute. You have to unmute.
Unmute karo.
You have to
Sir.
unmute. Unmute. Unmute.
Yes, very good evening to everyone there, and I'm very thankful to Professor Hosur, along with all our my HBNI colleagues, for giving an excellent lecture, covering a very broad canvas, starting from fundamental principles to applications, very advanced applications. I'm sure this will give a very good taste to the students. It is like the soup before a full dinner. Now the various components they can enjoy individually as the course goes on. I congratulate IPNI for organizing this course, and I'm sure that it will be extremely popular and it will be very useful to the research students as well as those who are getting initiated in the subject. So thanks once again, and I'm very happy that I was able to join this program. Through this, I also expect to learn a little bit about NMR spectroscopy. I have not studied it formally. Thank you very much.
Thank you. That is our former Vice Chancellor. We used to encourage these kind of topics to be covered in HPNI. So, shall I expect a few words from Professor Ghosh?
इसका कर सकते हैं. So very good evening to everyone. So Professor Naik told that why we are introducing this course to HBNI, and then Professor Paul told about gave the overview and told what are the different modules. And I think Professor Hosur has taught the full course today. So I think your each slide will be a class. Yes. So I'll tell the students that you may consider that each slide Professor Hosur has shown today will be covered, let us say, maybe 1 hour or 2 hours. Some slides may take 3 classes. Okay. So I think all of you will enjoy. So why I am telling you that this course is very special. See, this course is now being taught to almost all master students and PhD students. Okay, so then what way this course will be different? First thing is that if you see the teachers in this or those who will be taking classes, they are actually using this, let us say, the technique for their day-to-day life in the research career. Okay, so whatever kind of their experience, either in the development, like Professor Hosur showed you a slide where he has shown that he has developed so many say pulse sequences or techniques to resolve the structure. Similarly, being a organic chemistry person, I will say that how I have utilized a routine NMR spectra, a proton NMR spectra, a carbon-13 NMR spectra, or a simple 2D NMR spectra, and to analyze or get the information of the structure. See, many times, see when you do a reaction in a lab or you isolate something, you immediately run a NMR, because that is the only technique which can give you a better information than any other spectroscopic technique, except XRD, that I'm not going to tell that, because XRD also there are a lot of limitations because the material has to be a crystalline solid. Otherwise, the first thing that you can get a good amount of information about the structure, even from a simple proton NMR spectrum, not like the structure Professor Hosur showed for proteins. But if you take a reasonable size small organic molecule of a molecular weight of, let us say, 1000 Dalton or so, you can actually get a reasonable structure analysis from the carbon-13 spectra or a proton NMR spectra. And there you have to understand how the different protons are coupled to each other. That gives you a lot of information about how the protons are distributed in space. So that will give you a 3D structure, their stereochemistry, their conformation. So that kind of the experiences of these teachers will be used in this during this course. Not only these small organic molecules, you will see the expert will be teaching you the solid state NMR spectroscopy, and then also you will see the experts who deal with nuclear magnetic imaging techniques. Okay, so I think that is the way it will be different from the regular NMR courses which is offered in the many of your academic institute. And I wish that all of you will enjoy the course, although it is a little bit longer. It is about 80 to 85 hours, but I think all of those who are really interested will enjoy this course. With this, I would like to thank who have joined online, the students, teachers, and everyone who have participated in this program. Thank you very much.
Thank you, Professor Ghosh, regarding your remarks. We request either participant to have some remarks on the course. Any online participants? Mr. Sonanda, Mr. Rebecca. Please. So now I request Professor P. D. Nayak to declare the course on advanced NMR spectroscopy. So may I request now Professor D.K. Maiti to propose the formal vote of thanks.
Good evening. First of all, I must thank Professor Hosur for accepting our invitation to give lectures, a few lectures, and especially today's this talk on inaugural function. I think he has, as mentioned by earlier people also, he has covered the entire NMR spectroscopy in a nutshell. So each slide, as mentioned by Professor Ghosh, each slide will be a lecture, 1 hour lecture that will be discussed on time. And I thank all the lecturers and especially the steering committee who has designed this course. This unique course is designed under the chairmanship of Professor P. D. Nayak, who is the Dean HBNI and Vice Chancellor officiating. Then Professor Paul, who is the convener of this steering committee, who is Associate Dean. Professor Arindam Ghosh from NICER, Professor Sunil Ghosh, Associate Dean HBNI, Professor Sudarshan from BARC, Professor Amit Chaudhary from Tata Memorial Center. So these are the members who has designed the course, and the speakers, as you can see, the speakers are also from different units of DAE. As Professor Hosur has initiated, he will also giving a few lectures. Then to start with, Professor Arindam Ghosh from NISHAR, who will give the theoretical background and to start the NMR course. And Professor Jagannathan will be talking from AIMS New Delhi. He will be talking from application side. Professor Amit Chaudhary, Tata Memorial Center, he will be also talking on application side. Professor Ghosh has mentioned from the organic samples how it is analyzed. Professor Sudarshan will be talking on solid state NMR, and Sondeep, they also from BARC, they will be talking on NMR other aspects. So I sincerely thank on behalf of HBNI for accepting our invitation and giving lectures in this course. And I also thank Professor Basudev Rao, our former Vice Chancellor, who was always interested to start such new course and keeping in mind the expertise available in different CIs of HBNI as well as other units of DAE. I think this has happened, as I mentioned the names of the speakers, they are distributed across different DAE units, especially under HBNI different CIs. And I also thank our IT team who has made it possible to broadcast this particular inaugural program, and who will be the key person behind all the lectures. They will be in the backbone broadcasting, covering the lectures and broadcasting it to all members. And I also thank all the students, 140 students who has registered, student or faculty members who wants to learn more about this NMR spectroscopy, for registering, is showing interest and registering for this course. And of course, I thank Professor Paul especially for taking care of everything. Thank you all.
Thank you, Professor Maiti. May now request our officiating Vice Chancellor and Dean, Professor P.D. Nayak, to declare the course on Advanced NMR Spectroscopy hosted by HBNI to declare open.
Good evening, everyone, and thanks for joining these inauguration programs. As Professor Pierre Rosler rightly mentioned, this is just a soup, and we'll have each part of them will be covered under different topics, which is explained by Professor Sunil Ghosh. The course is going to start from tomorrow onwards. First few lectures will be taken by Professor Arindam Ghosh from NISHAR, because unless until the theory part and spin and other related things, which is very important to understand the NMR spectroscopy, we will deal with that fundamentals. And with that, I declare that this course is open now for all the participants and going to commence from tomorrow onwards. With this, I thank everyone who are registered for this course, as well as all the faculty members and all those who are joined either physically or online for this inaugural programs. Thank you all.
Thank you, Professor Nayak. With this, we are coming to the close end of the function. It is all raised for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Very thick soup. Professor Narasimhan actually taught us NMR.
And that time,
And that time, Sumitra